So my name is Dan. I'm not going to be talking about relational data today, so if you do want to hear about relational data, we have a talk in the main conference. But I'm actually going to talk a little bit about how we evaluate causal models. And this title is sort of intentionally obvious. We'd like to evaluate causal models by comparing interventional distributions, but that's not really what we're doing right now. So let me just start with some of our findings, some of our key contributions. How we're evaluating causal models right now doesn't really characterize the full causal discovery pipeline. We're primarily focusing on evaluating causal structure, but ultimately the way that we want to use causal models is in terms of interventional distributions. So one way we can start thinking more rigorously about interventional distribution quality is to shift to a focus on statistical distance rather than more qualitative measures on graphs. So in this talk, I'm just going to show an example of one of those statistical distances, how we can use them to evaluate interventional distributions. And I'm going to show that the conclusions you'd reach doing a causal investigation can be different using statistical distance rather than using a graph-based distance. So in terms of general structure of the talk, I'm going to start with a broad overview of the types of models that we're thinking about, and Frederick gave a great introduction, so I may not need to spend a whole lot of time there. I'm also going to talk about how we do evaluation right now, so the current measures that are used to evaluate causal models. Finally, I'm going to talk about our proposal, which is to evaluate with statistical distances on interventional distributions rather than evaluating in terms of structure. And then I'm going to compare the two evaluation approaches. So I'll start with a bit of an introduction to causal graphical models. The models I'm going to consider in this talk are parameterized directed acyclic graphs. So here I've just given one sort of example parameterization where we have some normal 0, 1s causing W and Z. And the types of interventions we're considering are given by the due calculus. So we may intervene on X, replacing its probability distribution with a constant. And then the causal inference task is to reason about how that affects W and Z. And of course, this is much more interesting with larger causal diagrams, but I wanted to keep things fairly small and concise for this talk. So there are two use cases for causal models. One is sort of qualitative in that we'd like to know whether intervening on some variable X influences another variable Z at all. Another approach is to actually estimate and evaluate interventional distributions. So we'd like to get a conditional probability of Z given that we've applied an intervention on X. And I'm going to focus on the second use case here because I think it's strictly more general than the first. You can use an interventional distribution to infer the answer to the first question. Now, I'm talking about evaluating causal structure learning algorithms. So these are algorithms that would produce the sorts of models I've shown on the previous two slides. So a few representative examples of this. One is the PC algorithm. This uses conditional independence tests to uncover constraints and use those constraints to then constrain the joint causal structure. Another is the GES algorithm. This uses a score-based criterion to identify the locally optimal structure, in doing so identifying the globally optimal joint structure of a causal model. And the third is a hybrid of the two. The MMHC algorithm uses constraints in some parts of the process and uses scores in another part of the process. Finally, I want to make it clear that we do really need quantitative evaluation for causal discovery algorithms because there's great uncertainty as to whether these work well in practice, whether there are certain domains or certain attributes of domains that lead to better or worse performance. There are also quite a few algorithms out there at this point as well. Like I said, we have three categories. We have constraint-based, score-based. We have some hybrid of the two things. So determining which algorithm is most appropriate in a given circumstance is something we really need evaluation to tease apart. So I'm just going to give an introduction to how evaluation is done right now. One of the most common techniques is known as structural Hamming distance. Alternatively, you can think of this as a precision or recall evaluation or true false positive rate. in essence, what I'm getting at here is that often people evaluate causal models by looking at edge inclusion or exclusion and sort of computing almost like an edit distance on graphs. So if we have the true graph in the upper left, one way we can be wrong is to underspecify a model. We can include fewer edges than there really are. Like here, I've excluded the edge from x to z. So that is one error unit. Another way we can err is in overspecification. So if I add an edge from w to z that wouldn't otherwise be there in the true model, that is another error unit. Finally, if I misorient an edge, if I have an edge from y to z in the true model and then I go from z to y in my estimate, that could either be 1 or 2 errors depending on who you ask and how you compute this. So there's a good commentary and result by Peters and Buhlmann recently. They basically showed that the structural Hamming distance doesn't really correspond to the quality of a causal model, because swapping an edge or removing an edge can have all kinds of crazy effects on a causal model, or not crazy necessarily, but all kinds of significant effects on a causal model, not all of which are directly related to graph edit distance. So their insight was that the best way to, or a better way to evaluate causal models is to count the number of misspecified interventional distributions, or count the number of interventional distributions that are biased, or would be biased if you had an infinite number of samples. So the computation of structural intervention distance, or SID, is somewhat different than structural Hamming distance because it requires using ideas from do calculus and adjustment, causal adjustment. So I'm not going to go into detail here, but I just want to show you how the two can differ. So again, if we omit this edge from x to z, that causes an underspecification error in structural Hamming distance, so that's one error unit. It's also one error unit in structural intervention distance, because now we've misestimated the x to z interventional distribution. So they agree on that part, at least. If I overspecify the model, that doesn't actually yield a biased causal estimate. It might increase the variance in finite sample settings, which I'll show, but the structural intervention distance counts the number of biased conditional probability models, and that one is unbiased, so no error there. And finally, things can vary somewhat dramatically with misoriented edges, because that can really cause lots of sort of upstream problems. So here, what would otherwise be, this should actually be structural Hamming distance is 1 or 2, and structural intervention distance is 3, because now I've misestimated the effect of x on y, I've misestimated the effect of y on z, and I've misestimated the effect of z on y. So this one model error has all kinds of bad effects in terms of causal estimation. So, like I've shown, like I've mentioned, there are some problems with using structural distances. They don't really carry through the full causal inference pipeline. So, in order to do causal inference, we need to learn a structure, we need to parameterize that structure, and we need to do inference on that structure in order to estimate the effects of an intervention. So, some interventional distributions can be more biased than others. So I can remove an important variable from a model and have a much bigger effect than if I was to remove an unimportant variable from that model. So if I'm dealing with finite sample settings, variance can be quite important. And so I can imagine circumstances where it's better to have a biased model without much variance than to have an unbiased model with high variance, because I have very little data. So a little bit of commentary on how model errors can induce statistical biases and variance. In the first case, I have an underspecified model where I've omitted an edge from x to z. And in the second case, I've omitted an edge from y to z. Now, in the conditional probability model of z, x is 10 times as important as y. So the first underspecification would be a much bigger deal than the second underspecification, but as measured by Hamming distance and intervention distance, these model errors are both the same. So this is a problem. We'd like to be able to say this category of model error is worse or better than another category. And here's a case where structural intervention distance fails to really characterize what will happen in a finite sample setting. So here I've overspecified the model by adding an edge from y to w and adding an edge from z to w. So now in the estimated model, w has 3 parents. In the true model, w has 1 parent. So in a finite sample setting, an estimator is going to have higher variance using the model on the right than using the true model. We'd like our models to be sparse, but intervention distance is really focused on biasness or unbiasedness, so it doesn't characterize variance. So I want to give a simple approach to evaluation with a statistical distance rather than a structural distance. And we need 3 things. We need model structure, and that model structure needs to be parameterized, and we need an inference algorithm, which we can use to obtain an interventional distribution, an estimated interventional distance in the model. And then we need a way to compare that estimated interventional distribution to a true interventional distribution. So that comparison is going to be done with total variation distance in our work. So the interpretation of this equation here is really that it's comparing an estimated model, p hat, to a true model, p. And we're comparing the effects of an intervention on the t variable, perhaps a treatment, on some outcome variable O. And we're just tallying up the differences between these 2 conditional probability distributions. I've shown this for a discrete model, but it generalizes quite easily to continuous models as well. Now, that estimand is for a specific treatment and outcome, a specific pair of treatment and outcomes. If I want to evaluate an entire DAG, an entire directed acyclic graph, you actually have to enumerate all pairs of vertices and compute that interventional distribution quality on those pairs. So that's expensive. Enumerating all those vertices is expensive. I'd argue that it's only as expensive as using the model. So if you really do care about all of those pairs of variables, then when you go to use the model, you're going to need to compute those interventional distributions anyway. So I'm advocating for something that is as expensive as using the model. If you have sort of a predefined set of treatment variables and outcome variables, then one principled approach would be to simply evaluate on those pairs of variables instead of all pairs of variables in the DAG. So now I'm going to compare the 2 alternative approaches, structural and statistical. We have 6 domains in total that we're going to be thinking about. 3 are just 3 very common synthetic data generation setups used for causal data evaluation. One is logistic data. This has all the variables here are binary. Every node is a logistic function of its parents. There's also linear Gaussian data. This is real valued data, conditionally normal vertex values. And then we have Dirichlet data, where we're generating discrete data where the conditional probability model is sampled from a Dirichlet distribution. We also have 3 real domains. We ran experiments on Postgres, which is a database server, the Java development kit, and networking infrastructure web platforms. So we ran a factorial experiment, all combinations of treatment variables, measured an outcome under each of those configurations. That gives us a true interventional distribution. We can then bias the data to make it look observational and evaluate how well a causal inference algorithm can perform on that biased observational data, comparing it back to the original experiment. So giving sort of an illustration of that, we start with this full data set where we have multiple records per subject. We've executed an experiment on each subject for each value of the treatment variable. So what the interventional data gives us is the full interventional distribution. We then sample that data to make it look observational. So we're inducing dependence with some confounding variables. We use that observational data in the structural learning process to get an estimate of a directed acyclic graph. We parameterize that graph. Then we use that parameterized graph to estimate an interventional distribution and compare that back to the original experiment. So sometimes people start with observational data, build a parameterized model, go out in the field, run the experiment, and compare that to the original model. This is sort of an inversion of that process because we start with the experiment. So I want to show a comparison between the structural measures and the statistical measure. So here I have two categories of models. I have underspecified models and I have overspecified models. And I'm showing here, for instance, that structural intervention distance is always 0 for an overspecified model. This is just by definition. These overspecified models are unbiased. Now, structural Hamming distance treats all edges as having equal weight, whether they're overspecifications or underspecifications. And so one of the most notable things here is that the effect of overspecification as measured by total variation distance is often much smaller than the effect of underspecification. So it's better to have more edges in your model than you need, which is something that Hamming distance doesn't really tell you. But it's also not ignorable to overspecify your model. So intervention distance says all overspecifications are fine, 0 error. As measured by total variation distance, that's simply not true. So these are some of the relationships that we can pull out of this evaluation and say, total variation distance really is measuring the effect of an overspecification in terms of finite sample model quality. And the effect of overspecification and underspecification are not really the same. Now, we evaluated these three, we ran evaluations on these three evaluation measures on these three synthetic domains and on the three algorithms I introduced originally. So we have the GES algorithm, the MMHC, and the PC algorithm. And one of the things we can see by running this evaluation is that the relative ordering of the algorithms is different from the structural measures to the statistical measure. So GES in particular performs quite well when measured by total variation distance. It performs moderately well to badly as measured by interventional distance or Hamming distance. Similarly, MMHC does not do well from a statistical perspective, but does okay or best from a structural perspective. This is a bit of a tangent, but it was an interesting result. So if we look at the difficulty of these data sets or the quality of the models learned on the synthetic data sets compared to one of our real data sets, Postgres, we can see that the real data set is significantly more challenging as measured by total variation distance than the synthetic data sets. So this is mainly just demonstrating that there is really a need for real-world evaluation and challenging real-world evaluation, and there's perhaps a bit of a gap between the synthetic models we're generating right now and the complexity of real data. So to conclude, the way we're evaluating causal models right now does not really capture the full end-to-end pipeline of causal inference. We can evaluate fairly straightforwardly the quality of interventional distributions using something like total variation distance. And this can lead to different conclusions about how well algorithms are working. So we can do it. It's, in principle, better or captures more of the pipeline. And it has been shown to produce different results. So thank you.
Thank you much, Dan.
Could you, maybe you said that, but I missed it. How did you handle equivalence classes?
So we enumerated equivalence classes and averaged performance across all the members. In practice, we were able to enumerate them because they were fairly small. I think more generally, you could sample from them. But ultimately, what we're trying to get at is an analyst would need to ground their analysis in a specific DAG and then compare results across DAGs.
Thank you.
Thank you very much. So another one. Thanks. Good talk. My question is, I'm not a very good theoretician. I'm very applied. And my question is, so for instance, one of my problems right now is I'll get 1 billion log events a day. And each log event will have, 150 variables in it. And I need to, sift through all that data and find the causal relationships. What I'm doing right now is I'm saying like, okay, here's a few things that I'm tracking. And what are the things, running PCA on it and saying like, oh, okay, these 6 variables are ranking high on my PCA analysis, saying like, those are the places where we need to be looking for causal relationships. What I'm trying to figure out from this talk and the previous talk is, what am I doing wrong? Like, what should I be doing? Like, it sounds like PCA is sort of like taking a, a knife to a gunfight, but I'm having a really hard time going from PCA to what you guys are talking about. And so how do I do that?
I think it all starts in trying to analyze what the causal question is that you're after, because so much of causal inference is saying, what are the variables that I would need to adjust for or account for in order to obtain an unbiased causal estimate of some quantity. So starting by saying, here are the variables I need to, I want to estimate an intervention with respect to, and here's the set of variables that would likely confound that analysis. And you can read up on Unipearl's work, especially on like the backdoor criterion and adjustment sets, and then identifying what those adjustment sets are. Because the foundations of this approach are to say, have you correctly identified the adjustment set? Some may be better than others.